All right, welcome back to the third part of nuclear magnetic resonance. I know that you're having fun because if you weren't having fun, you wouldn't have came back to listen to this lecture. Or maybe you just have to listen to this lecture in order to get a good grade. And if so, that's okay too. I don't blame you. So NMR, nuclear magnetic resonance. In the previous videos, we discussed this concept of applying a magnetic field onto these molecules in order to, attention, get them all to line up, right? So here's the nuclei, and they're spinning in all directions that they want to spin into. And let's say that we, attention, put the magnetic field onto the nuclei, and they all point in the same direction. I oversimplified this, folks. You knew I was going to oversimplify it because I told you in the very beginning I was going to oversimplify this thing. Because it is not our intention to be experts. It's our intention just to become familiar with the concept of NMR. So when we apply the magnetic field, I'm going to put in big capital letters up here at the very top. Most, and I'll repeat, most of the nuclei will point in the same direction and spin with the field. That's what we call that, with the field. However, here's the problem. You know as well as I do that not all of them are actually going to do this. We are going to have some rambunctious, rebellious kids that are out on the playground. And when the teacher goes outside and says, "Okay, everybody, come on in, recess is over," the majority of the nuclei will line up and the majority of the nuclei will go back into the classroom. But there's going to be a few problem children that's still out there in that playground. And those problem children are nuclei, in this case, that spin in the opposite direction. Right? We're going to have some that's going to do it. Children behave, but some children misbehave, and they get a kick out of doing it, like me when I was younger. So the nuclei will spin in what we call against the field in this case. Now, not a lot of them will do that. Very, very tiny amounts of children will misbehave on the playground. The majority of them are going to listen to the teacher. But you do have a couple in the classroom that's going to think it's fun and games out there, and they will not come in, and they're just asking for a spanking, if you can still give them spankings in school today. But you can't. That's kind of a shame. All right, so 20 out of about 1 million will go against the field. But we do have some that go against the field here. They spin in an opposite direction. Sometimes people will call this a parallel direction, and sometimes they'll call this anti-parallel direction. Sometimes they will call it clockwise for the normal kind of tendency, and counterclockwise for the opposite spin. Whatever the case is, it's okay. There's two terms that are going to be out there that explain the way that these nuclei behave. However, we do have one term set that we use here that everyone pretty much understands, and this will be called the alpha spin state, and this would be called the beta spin state. So when you apply a magnetic field, attention, all the nuclei line up, they all point in the same direction, and the majority of them spin in the alpha rotation. We do have some that spin beta. So they go opposite or backward of the majority of them. Not very many of them will do this. Again, 20 out of 1 million molecules will do this, give or take a little bit, but we do see this tendency that's out there. All right, so I just want you to understand that this is not simple. This is somewhat more complicated than how we're describing it, but that's not our intention with these lecture videos. So let's talk about the thing that's so special with the alpha and the beta spin states. All right, so if we go back and we go and take a look at this swing set, and I'm going to be behind this kid that's very lazy, that deserves a little bit of punishment here. And I begin to push this kid on the swing, once again, back and forth, back and forth, back and forth, back and forth. Well, we've already said, sometimes we will push the kid so hard that this kid will flip upside down. And they begin to scream. And that scream is going to be given off in some type of energy, because once again, the energy that goes into the system has to come out. Law of conservation of energy is basically upheld in this situation. So if they scream and we release that energy and stop it, eventually they will come back down to their original spin state. In other words, kind of the beta spin state would be the kid that is kind of already starting upside down here. Very few of them are going to start upside down. The majority of them are going to start normal, but we do have some that will flip upside down in the very beginning, and then we can continue to push them, and as we push, they will go back down to the normal kind of standard swing set, if this is the way that we want to think about it. This pushing, like we've said before, it's a resonance, but we have a special term that we do use here, and that's called RF radiation. So we are putting RF radiation into this system, and this is starting to push the children on the swing and trying to get them to turn upside down in a way so that they can scream, release the energy back off, and then we can pick up those screams on our side. Now, how is this even related to what we're talking about? Well, the reason that I'm mentioning it is because there is a situation here that we can talk about that relates this law of conservation of energy to alpha and beta spin states. So the majority of the children will start off with the alpha state, and that's here, and they are on the swing and they are acting normal, but yet they're still lazy. So we begin to sink in RF radiation in the form of energy, or waves, light energy in a way. And this alpha spin will basically start to whipple wobble, and then sooner or later the kid turns upside down and alpha state now goes to beta spin state. So they are upside down at this point. They begin to and then as they do that, they release that energy back off, and that energy is picked up by our instrument of the NMR. As they release that energy, the swing basically comes back down to the starting position, and alpha state is achieved yet again. So then we can continue to do this if we want. Alpha goes to beta, beta goes to alpha, alpha goes to beta, beta goes to alpha. All at the same time, when they begin to flip, the alpha goes to beta. That requires energy. Once beta hits, the molecules release that energy, they go back down to where they start, and that energy is given off, and that energy can be picked up by our instrument. All right, so this is kind of the concept of spin state, alpha, beta, and basically RF radiation, which gets the whole thing to kind of do its job the way that it needs to do it. Okay, so something else that we need to talk about here in the world of NMR is something called shielding. Now, shielding's very important. Shielding is going to help us determine the type of structures that we have and the way that these kids are hooked up together. Are they in a line? Are they in a chain? Are they getting branched off? What's going on with them? So I want you to imagine now a playground with a bunch of swings, not just one. Okay, so there's a swing, and here's a swing. And we've got a really lazy kid here, and a really lazy kid there, and a really lazy kid here, and so forth. So what you need to understand is that molecules are very similar to this. Not all kids are going to be the same. And this is the same as for molecules as well. So for instance, a lot of people have a question, well, wait a minute, we are focused on hydrogens, right? And all hydrogens are the same. They all have one proton, they all have one neutron, they all have one electron. You know, what's going on? Why are we getting different signals from protons? Because they're all protons, right? I mean, they're all kids on the playground. So why are we getting different signals from them? And the reason is because the kids slightly scream differently. This one can go, ah, and this one can go, ah, and this one can go, ee, right? So they all scream in a different way, very slightly, and it's all due to their neighbors. So the one here in the middle, well, this one can scream when we turn them upside down, and this one will scream based on what is neighboring them. So if they begin to flip and they all begin to flip and they all come back down and they all begin to scream, they might be a little bashful. So depending on the number of neighbors that they have, they might scream in a different way. And their screams could be shielded almost with the ones that are neighboring them, especially if they're screaming too. So as you can imagine, if you're here standing on this end and you are listening to these screams, this one on the end, you will probably be able to hear a little bit better once they flip and come back down to their normal position. They're not getting drowned out by anything that's beside of them except for you. Well, if you're trying to listen to how this one in the middle is screaming, that one's going to sound a little different, because you might get some sound from this person when that kid screams, and you're going to get a sound from that kid when it begins to scream, and it's a little further away from you, so therefore it might be harder to pick up in a way, right? And then down here on the third row, this one is even further away, and that furthest kid that's sitting on that swing set might be a little bit more difficult to hear because they have neighbors as well. So it's all about the neighbors. It's all about the kids or the atoms that are beside of each other in the molecule. And this is what shielding means. Shielding is basically this idea that molecules have what we would call a cloud of electrons, right? And this cloud of electrons can do things to a molecule, if we are not careful, to make it different. The protons behave differently depending on where it's at in the molecule. All right, so let me clear this up and bring a little bit of chemistry into this, right? So CH3, CH2, CH3. Let's take a look at this simple molecule in a way, and we'll look at this thing and talk about the kids, or the atomic nuclei for hydrogen that's going to be located here. Here, this carbon in the middle, it's got some neighbors. It's got some neighbors here, and it has some neighbors there. So this would have a signal, and I'm just going to randomly call this signal A, okay? It doesn't really matter how we're doing this right now. We just need to understand differences here. That's all that we're after. This carbon on the end, this has 3 hydrogens, and these hydrogens have one neighbor on the swing set, and that one neighbor means that this signal is going to be a little different. And the reason is because it only has one neighbor. That's it. The one in the middle, it's got 2 neighbors. So it's in a different position. So that will have a different signal in NMR. And then finally, the one here on the end, well, it's actually just like this one here on the end. There's no difference. It has a neighbor of CH2. This one has one neighbor of CH2, and they are what we would call equivalent or identical. All right. The same thing would happen here with CH4. CH4 has no neighbors. It is a kid on a swing set by himself. And all of these hydrogens are equivalent. That is what we would say. And because of that, this would have one signal, and that is it. If I go on to CH3, CH3, right? We have 2 carbons that are connected together. Each one of these have 3 hydrogens, 1, 2, and 3. All of these hydrogens have a neighbor, just one, and it's a CH3 group. And then all of these hydrogens have one neighbor, just one, and it's a CH3 group as well. So we would actually get a signal from those hydrogens, and we would get a signal from those hydrogens, but actually it would be the same signal here. And the reason is because they are equivalent. However, in the example up at the top, they are going to be more than one signal. And the reason is because this middle carbon is different. It has a neighbor to the left and a neighbor to the right. When the ones on the end, They only have to deal with that one nosy neighbor to the left hand or the right hand side of them. All right. So this would give us two signals in total. This would give us one signal in total. And this would give us one signal in total. If I go to CH3, CH2, CH2, and CH3, how many signals would we get here? Well, this carbon has one neighbor, and that is it. So we would get a signal there. This carbon, well, it has two neighbors. It's got a neighbor to the left and it's got a neighbor to the right. So this would be another signal that we would get from this molecule. And then we go to this third carbon in the line. But folks, look at this third carbon. We've got a neighbor to the left and a neighbor to the right. And that neighbor to the left, or on one side, is a CH2. And the neighbor on the other side is a CH3. Well, that's the same as this one. This carbon experiences a neighbor of CH2 on one side and CH3 on the other. So therefore, these would actually be equal to each other. They would be an equivalent signal. And then finally, here on the fourth carbon in the row, we're at the very end. It has one neighbor only. That one neighbor is a CH2 group. That one neighbor is a CH2, just like on the very first carbon, that one neighbor was a CH2. So therefore, this one is actually the same signal as the one in the front. So here we would get only two signals as well. It's all about where these hydrogens are located in the molecule. So this will give us an idea of the number of signals that we will experience in an NMR spectra. And this is how we determine the actual separate signals that we would get from a molecule. Now, we can go a little bit further. And when we go a little bit further, I'm going to look at how many hydrogens are equivalent. All right, so if you take a look here, this is one signal and this is one signal. Now, the problem here is that this carbon has 4 hydrogens that are all the same, and this molecule has 6 hydrogens that are all the same. Well, there's more hydrogens here, so the intensity of the line, the height of the line, will be much taller in that NMR spectra. So that's where I'm going to stop this video. We've talked about the number of signals and the intensity, or how high these peaks might show up in the spectra. And in the next video, we'll talk about shielding a little bit more.